himself, who's been moderating some of our sessions. I'm sure you've been attending them. Now he's making a presentation on optimization of VHT for buildings. For all those people who are joining now, I would like to introduce him. Krishna Kumar Ravi is the President and CEO of PAPL Corporation. He's a mechanical engineer by qualification. He joined Otis Elevator Company as a graduate trainee, engineer trainee, and was trained in erection, testing, and commissioning of elevators. After a successful tenure in sales and installation, KK moved to Mitsubishi Elevators, where he handled Tamil Nadu and Kerala. He joined PAPL in 2009 after spending close to 11 years in the elevator industry. PAPL is the first and only accredited inspection body in the exclusive domain of VHT industry. So over to you, KK, and I hope that everybody enjoys his presentation and have a lots of takeaway from that. Over to you.
Thank you very much, Anita. There is no business conclave without a traffic analysis or elevator related subject or a presentation. So I'm not going to do a stereotyping or a typical traffic analysis presentation. I'm just going to try and present to everybody how the elevators can be optimized, or what are the considerations that one can make when they're deciding on the elevator traffic study. So can I start with my presentation now?
Yes, you can. No?
Okay. Now, we are going to dwell upon the intent and the means. Why an elevator system should be optimized, and what are the means to optimize the elevator systems in buildings. Now, the discussion topics would be: what is the current standard approach to vertical transportation design, and what is the need for optimization? Then what are the benefits and risks, and how are you going to achieve this optimization? Then we're going to have a small case study, and we're going to have a conclusion on how this works. The standard approach to vertical transportation design is, it starts with understanding the purpose of the building and the circulation within. This is a standard procedure. Everybody goes through the building, it goes the purpose of the building, and they understand the circulation within. Once that is done, the standards for that particular design are established in terms of the quality of service and the quantity of service. Once that is done, generally the population is calculated based on certain set parameters that are provided in the NBC, as well as based on what the customer's intent for that building is. Then the selection of the elevator parameters happens in terms of what is the speed, what is the acceleration, what is the deceleration, what are the door dwell times, and what are the group control systems and all that. Then we simulate the traffic using softwares, and then we come up with results. We iterate to have multiple options, and then we publish or recommend the results that are viable in terms of meeting the standard requirements of either NBC or the IS or any other standard to be particular. But why is there a need to optimize? Because every building that comes up is not same. Every building requires a unique approach. Every developer's needs are different. At the same time, there's a very high requirement on cost optimization, because real estate is very expensive. The more you optimize on the vertical transportation, the more the builder saves. A standard design approach may not lead to an optimal design. It just meets the design criteria set forth by the standards, but they may not be optimum solutions. And they lack creativity. And hence, a standard design would only be a kind of a calculator approach and not a designer approach. Now we have, let's look at the benefits of optimization. The benefits of optimization starts with reduction in capital investment. You save the number of lifts, or save the capacity, or save the speed, reduce the speed. It saves directly the investment that the developer makes. It reduces the hoistway space. Maybe it adds on to the sale area that the developer would benefit. Then that's what it increases the leasable area. Then there's a year-on-year addition to the rent from the area that is saved. Then there's a reduction in cost of maintenance on the equipment. The reduction in operating cost. That is your cost on power, the cost on many other housekeeping and other related things is all saved. Then assurance on the design being within the regulatory framework. So all this design that is being done, keeping optimization in mind, would still continue to be within the framework of the standards. Now the risks. There's a risk that maybe at a later point when you've optimized, the building could be overpopulated, which would lead to inefficiency and frequent breakdowns. This can happen, but these breakdowns may also lead to overload or malfunctioning of the units. So these risks may be rare, but they have to be kept in mind because they might create an inefficiency in the building's functioning itself. Nevertheless, they have to be addressed as well. Now let us look at how the elevators can be optimized. The optimization starts with, let us look at the area optimization. To start with, every builder would want to show that their building can be populated to the brim. This is a general tendency because any person who wants to rent out a building wants to look at how many people he can populate inside the building, and the builder would want to show the efficiencies in the building, the floor efficiencies, that they are high and so many people can be occupied. Nevertheless, the most important thing is in reality that may not be possible because there are certain areas which cannot be populated, or the population that is there in the building actually uses those spaces and does not permanently occupy those spaces. For instance, spaces like lobbies or your toilets or your pantries or your food courts, these are all spaces that are actually used by the people that who occupy the office space. So it is not that you have a separate set of people staying there and staying here who will actually increase the occupancy in the building. Now we have three areas that are shown in the screen. The first one is the usable area. The usable area is the most preferred area for any traffic analysis. This area excludes the core and includes only the area that is actually used for the office purpose. Maybe a further refinement of this would be setting a layout, which would be the best way to establish the population. But in the beginning stages of the project, that would not be possible, and hence we may use certain rules that have been specified in the NBC and IS to estimate the population. The second is the built-up area. The built-up area includes all the spaces that have been built, but excludes all the shafts, cutouts, or any other spaces that are hollow. Whereas a saleable area is the area that includes all spaces within the boundaries of the building. This is what is the most ideal space as far as the builder or the developer is concerned, because he can actually estimate populations to the brim. Whereas in reality, that could be a deterrent in the number of elevators that may have to be procured. Now, if at all we start working on traffic analysis, the most preferred would be usable area. So we optimize the area and start using the area. Now, next is the population optimization. We have population optimization tables available in NBC, but I'm giving you a small guideline based on which the population can be estimated. The best way to do a population estimation is at 10 square meters per person, but there may be situations where the developer may want to have a slightly denser buildings where you can use about 7 to 8 square meters per person on the leasable, on the net usable area. In hotels and apartments, we can use about 1.5 to 1.9 persons per bedroom. Hospitals, 3 to 5 persons per bed space. That includes not only the patient, but also the support staff, doctors, and others. For schools, you can use about 0.8 to 1.2 square meters of the net usable area per pupil. And these estimates are the most optimum estimates, and they give you the right close to realistic occupancies. And the intent is, so long as you are able to design your buildings or the elevator systems to close to real values, I think you can automatically optimize the vertical transportation systems for the buildings. Now, there is one more very important aspect. You have estimated the population. Then, is it very important for you to take the full population? I feel it can be further optimized using certain available guidelines from Gina Bani, where you can actually discount certain population towards people who are coming early, who are latecomers, who are on leave, unfilled vacancies, and persons on outstation duties. These percentages have been arrived by us based on certain due diligence work that we have carried out across the country in various campuses. And these are average values, and these are close to realistic. And these values have been, we have documentary evidence towards these values. And hence, these are working well. And these percentages can be considered while uh, using populations for traffic analysis. This is one of the most key important key deductions that may have to be done while estimating population. And this is for the apartments. Apartments also have can also have some deductions towards unoccupied flats, people who are traveling, apartments with elderly people who may not use the elevators during the peak time, apartments that are not occupied to the design capacity. Maybe there's a 3-bedroom apartment and there's only 2 people living there, and people working in shifts who may not use the lifts during the peak hours, and they may require the service only during non-peak hours. This deduction also ensures you establish the adequacy based on the real-time situation. Now, there is also a case of peaks happening. With all officers, generally working with 2 shifts or 3 shifts, peaks can happen multiple times. And it is very important that you consider the dominant peak among the peaks to establish the traffic analysis. Once the elevator is designed for the dominant peak, it automatically gets addressed, the lean peak automatically gets addressed. So always design and look for dominant peaks, and maybe you can one can discuss this particular aspect with the building operator or the building promoter or the occupant to establish the peaks. Generally, what happens is in a multi-tenancy buildings, if you have about 10 offices functioning, in all likelihood, all these 10 offices might not have a similar pattern of office functioning. This is because no 2 offices have a similar culture. An IT company has got a different culture, a manufacturing company has a different culture, and hence these starting patterns also differ. Under these circumstances, it is prudent to always consider 2 peaks, maybe to be on the safer side. A dominant peak of 80% and a lean peak of 20% can be considered, so that whenever a traffic analysis is done, you're not overestimating the population. So most of the discussion here, the optimization revolves around how to establish and fix the population more than how to select the elevator. Even though there are ways of selecting the elevators, the primary objective would be to establish the right population before proceeding further. Now, as far as once the population is fixed, where do we go next? Next is to select the efficiencies. We have a range. Generally, most of the standards provide a range. So the minimum range that can be established has to be selected. Because, for instance, in office buildings of multi-tenancy, the Indian standard specifies 10 to 15%. Even selecting 11% means that you are increasing the efficiency by 10% and not 1%. 10 to 11% increase is a 10% increase in the design requirement. So any 10% increase would obviously have an impact on the elevators that are being designed for. So hence, it is very important and very critical to select the kind of efficiencies that you want to design the elevators for. Generally for office buildings, 10% should be sufficient unless it is going to be a specific requirement by a single tenant who is also the owner of the building. If it is going to be a leased out building or a building for multi-tenancy, it is always better to restrict the efficiencies to 10%, the 5-minute handling, peak handling efficiency to 10%. And always remember, your traffic should be considered only pure up peak, always. any for office buildings especially, because any cross flow or down traffic during the peak will be a deterrent to your optimization efforts. So hence always consider a 10% efficiency only and a unidirectional traffic flow. Now, technology also supports in this exercise of optimization. The first one is we have the following technologies here. First one is fuzzy logic. The fuzzy logic one, people call it by different names. You know, it is somebody calls it as relative system response, and this actually works on giving scores for the elevator that is most suitable. The highest scoring elevator comes and serves the particular call. That is how the logic works, and it works on various parameters. Various scorings are given, scores are given for every situation, and the elevator that scores the highest will come and attend to your call. Then there is an early car announcement, which is also called immediate prediction. This also has got certain advantages, but there are certain limitations also here. If somebody is holding the car in some other floor, the car announcement may be changed to a different car. At that time, there might be a chaos. And the next important control system is your destination control system with basic parameters. And the second one is an advanced system. Destination control systems are traffic boosters. They help improve the traffic systems. In office buildings where the number of elevators are 3 or above, better to choose a destination control system to optimize the equipment. Now, standardization. So standardization is very important for any developer. This ensures that your comparisons are very objective, and your decisions are also very objective. So you have to set standard parameters across in terms of what is the handling efficiency that you want for your projects. What is the waiting time that you intend to provide for all your projects? And the second thing is you always use standard capacities and sizes. Using standard capacities actually helps you understand various options. If non-standard capacities are used, then it becomes very difficult for you to do a comparative analysis or a study to take decisions. Strategize on common population densities based on net usable area. This you have to keep it as a standard for your design purposes. Maybe when you're leasing out the building, maybe for the same configuration, you can work out based on your sale area or something as a matter of submission alone, not for the design purposes. All designs should be based on net usable area only. Then include jump lifts for buildings that have 3 parking floors and above. The reason is by including jump lifts, you're actually reducing the cost on your main elevators. You need not go for more number of main elevators, which have higher speed and higher capacities. At the same time, and a different control system as well. At the same time, you're segregating the traffic between the parking floors and the main floor, and ensuring there is enough security, and at the same time, your efficiencies are not compromised. Because maybe 20% of the population of the building may be using the parking floors, and you might not end up making everybody wait longer, and just only 20% of the population may need to jump from the parking floors to the main lobby to take the main lifts. So hence it is very important to make such considerations. The variation, when you're standardizing the whole system, your variation should be only the speed, the number of lifts, grouping, and the control system. Rest all should be a standard parameter, which also helps you in setting some brand parameters. So I'm coming here to a case study. Let us look at a speculative building with ground plus 10. I'm not taking any basements here. With main entry in the ground floor, net built up area of 2,000 square feet, and a net usable area of 1,50,000 square feet. And we are considering a simple density of 100 square feet per person, or roughly about 10 square meters per person. So this is the estimate. What you see in blue, light blue, is area considered on the net usable area, net built up area. And what you're seeing on the right side is the population based on net usable area. If you look at this, there is a population that has been estimated at 2000 and this is a population estimated at 1500. You have close to about 25% reduction in the population here itself. And we are looking at a 80-20 start regime. This 80-20 start regime further reduces the population to 1,200. So when an elevator system is designed for 1,200, automatically the 300 people also will be addressed during the second start regime. Now, look at the results here. The results are very clear. When you use the nest built up area with 0% absenteeism and no start regime ratio, what you're getting is you're getting close to about 8 elevators of 884 kgs with a waiting time of 27 seconds, which is of course within the parameters of the average waiting time as set forth by the Indian standards. Whereas if you just shift it to net usable area with 80-20 start regime and 20% absenteeism, with a standard group control, you get 4 elevators of 884 kgs at 1.75 MPS. But when you shift it to DCS, you can reduce the capacity to 680 kg. Still, your parameters, your values are within the, in fact, your travel time reduces drastically to 45 seconds, which is very good. You spend, the passenger spends very little time inside the elevator. So conclusion for this presentation is the area consideration is the most crucial aspect of optimization exercise, which establishes the occupancy in the building. Estimating the higher right population ensures optimal requirement. Considering the correct judgment criteria, that is, your judgment criteria should be within the recommended parameters, yet it should be at the lower threshold rather than in between or the higher one, which actually optimizes the elevator design. Anything higher, even 1% increase in efficiency means that you have to increase about 10% values, and a 5-second increase in waiting time also means that you have to change the acceleration or speed or the number of elevators at some point of time. So thank you very much, and I think this session is a very brief session on how this is not a traffic analysis session. It is a session where you get into you get an idea about how optimization in elevators can be done for buildings. Thank you very much.
Thank you, KK. I'm sure people who have attended, if they have any questions or anything, they can write to you or reach out to you. Thank you so much for sharing this.
Thank you.
Our next session will be at 2 o'clock, which speaks about how intelligent should an elevator be. So I request all the people to join us back again at 2. Thank you so much.
Thank you. Thank you. Thank you.